Welcome to This Explainer. Today, we're going to unpack exactly how digital crime scenes are investigated in the real world. If you've ever watched one of those crime shows where the brilliant hacker traces an IP address in like 5 seconds flat, well, you probably already know that's not exactly how it works. The reality, it's much more complex, definitely more challenging, and honestly, a whole lot more fascinating. So why is catching a modern cybercriminal harder today than ever before? Well, there's a fundamental arms race happening right now just beneath the surface of the internet. We've got attackers literally hiding in plain sight. They're actually using the very tools designed to protect us. And on the other side, defenders are working tirelessly to uncover them. It's this constant, high-stakes game of cat and mouse. And the playing field, it's constantly shifting beneath our feet. Okay, let's map out the investigator's journey and see what analysts are really up against. We're going to walk through 5 massive roadblocks. First, the encryption dilemma. Second, the art of spoofing. Third, tracking moving targets. Fourth, the data storage bottleneck. And finally, navigating privacy laws. All right, diving into Trial 1, the encryption dilemma. This is basically the locked armored truck of the internet. Now, the crucial point here is that encryption is absolutely essential, right? It's what protects our passwords, our financial info, and our personal text messages. Essentially, it converts your data into a coded format. But here's the massive catch. While it does an amazing job keeping our data safe from criminals, it also creates a gigantic blind spot for forensic investigators because it hides the actual payload. Think about it like this. If an attacker steals data using a secure HTTPS connection, the analyst is essentially just staring at the outside of that armored truck. Sure, they can read the license plate, which is the metadata, things like the source and destination IP, the packet size, maybe the timing and protocol. But they are completely blind to what's actually hidden inside. They can't see the message content, they can't see any stolen files, and they definitely can't see the malware. And different encryption methods create very distinct headaches in the real world. Attackers use VPNs and Tor to obscure where they're coming from. Modern TLS 1.3, it keeps session keys completely unavailable. Even ransomware uses encrypted channels to hide its command communications. Because all that payload data is totally hidden, investigators have to get really creative. They adapt their strategies to rely heavily on endpoint forensics, basically looking at the devices themselves where the data is still in plain text, and they use behavioral analytics just to spot any weird anomalies. Moving right along to Trial 2, the art of spoofing. Let's see exactly how attackers use digital disguises to bypass security. So, spoofing is, at its core, simply pretending to be someone else in the digital world. And what's kind of terrifying is that attackers can fake almost any digital identifier out there. They can forge a bank's email address. They can poison DNS caches to redirect you to a completely fake website. They can spoof an IP address to sneak past authentication, or even spoof a local network's ARP messages to intercept traffic. It's wild. Now let's look at the exact methodology criminals use to pull this off. It's a very calculated 5-step process. They always start with information gathering to collect target intel. Then they craft that fake identity, forging headers or DNS entries. Step 3 is sending out that deceptive communication. Next comes the make or break moment, victim interaction. The user responds because they believe the source is trusted. And finally, step 5, the attacker achieves data theft or they gain system access. The mitigation for this trial is all about rigorous verification and filtering. You just can't trust a source at face value anymore. Defending against all this spoofing requires tools like DNSSEC to validate DNS records, or implementing things like SPF, DKM, and DMARC for email authentication. On local networks, it means enabling dynamic ARP inspection on your switches. The big takeaway here, always verify the source of the communication. On to Trial 3, tracking moving targets. Here, we face the massive challenge of a digital crime scene that simply will not sit still. In the past, traditional networks were honestly a forensic analyst's dream. You had static IPs, centralized servers, fixed user locations. If a device got compromised, you knew exactly where it was physically plugged into the wall. But look at mobile networks today. We're dealing with dynamic, constantly changing IPs, distributed edge devices, and roaming users. Evidence trails are now completely fragmented across Wi-Fi, 4G, and 5G networks. It's like trying to put together a giant puzzle while someone keeps moving the table. Let's see how this actually plays out in a real-world scenario with a mobile banking fraud case. Say a suspect uses public Wi-Fi and then switches over to a 4G cellular network to try and cover their tracks.
To catch them, investigators have to collect and correlate logs from the bank, the Wi-Fi access point, and the ISP. They match the dynamic IPs assigned to that exact device using its unique IMEI number. By piecing together those carrier logs, timestamps, and geolocation data, they can actually reconstruct the entire session. This proves a continuous user presence effectively tracking down a suspect who is constantly on the move.
Which brings us to Trial 4, the data storage bottleneck. This trial isn't about deception or movement. It's the sheer challenge of trying to drink from a multi-terabyte fire hose. 10 terabytes. Think about that for a second. That is the uncompressed raw data generated in a single day by just a standard 1 gigabit per second network. I mean, your hard drive is probably sweating just thinking about that. Storing full packet captures, literally saving every single 1 and 0 flowing across a network, is incredibly expensive and honestly mathematically unsustainable for any real length of time. So what actually happens in the real world when your storage server just fills up mid-investigation? Well, exactly what happened at this university lab. They were generating about 500 gigabytes of traffic logs every single day. Within just 20 days, their brand new 10 terabyte forensic server was completely full, which just totally halted all their data collection. If a major attack happened on day 21, they would have absolutely no record of it. Zero. The solution here is intelligent data management. You really have to make these strategic trade-offs between completeness and efficiency. So instead of full packet captures, you transition to selective data capture using tools like NetFlow, which just stores high-level connection summaries. Actually, for that university lab, doing this reduced their data size by a massive 90%. You also combine this strategy with data compression, tiered storage architectures, where older data automatically moves to cheaper cloud storage, and strict automated retention policies. And finally, Trial 5, navigating privacy laws. This last trial is perhaps the most sensitive of all. It's a very delicate tightrope walk of legal and ethical constraints. Network forensics, by its very nature, involves capturing some highly sensitive personal or organizational info. But investigators can't just go in and grab all the data they want. They are strictly bound by core privacy principles, like data minimization. This basically dictates that only the absolutely necessary data should be collected and stored for any specific investigation. No fishing expeditions allowed. And the legal frameworks governing this data collection, they vary wildly depending on your jurisdiction. In India, the IT Act penalizes unauthorized disclosure, but does allow government interception under very strict authorization. In the United States, investigators have to carefully navigate the Fourth Amendment, the ECPA for getting warrants, and the USA Patriot Act. Over in the European Union, the GDPR can impose massive fines if data isn't processed with a clear, lawful basis and strict consent. But the one universal rule across the board, investigators must always secure lawful authorization before they even think about analyzing a single packet. And that brings us to the ultimate question. We've seen how encryption blinds us, how spoofing deceives us, how mobility fragments the trail, how sheer data volume overwhelms us, and how privacy laws restrict us. That wraps up our explainer on the 5 trials of modern network forensics. But it definitely leaves us with this one provocative thought. As this constant cat-and-mouse game between attackers and defenders keeps evolving, how are we going to maintain the visibility we need to catch cybercriminals without sacrificing the privacy we all deserve? Thanks so much for joining me, and keep questioning the digital world around you.